probability can be used to figure out the outcome of a lot of genetic crosses. So we do want to invest some time into talking about the probability rules and then how we can apply those to some of the crosses and hopefully simplify some of our math that we're going to be doing in chapters 14 and 15. We will be looking at two different probability rules. The very first one that we're going to look at is what we call the multiplication rule. The multiplication rule states that the probability that two or more independent events will occur together is the product of their individual probabilities. So by independent events here, we're talking about two events whose outcomes do not really influence each other. So if we have event A, we take the probability of that, and we have separately event B's probability. We can take those two probabilities, multiply them together, and that will give us the overall probability that both event A and event B will occur. Now this is typically what we call our AND rule, because we want the probability that we're going to get event A and we're going to get event B. If you talk yourself through a lot of the problems that you're going to go through, the genetic crosses, you will find yourself saying and that is a clue that we're going to be using the multiplication rule. Now we've already used the multiplication rule a little bit. We didn't really think about it as the multiplication rule at the time, but notice if we look at this monohybrid cross right here. Now when we did this cross, if we just look at this very first box here and we say what is the probability, okay, so from these two parents, what is the probability of getting capital R, capital R? Now hopefully at this point you could just draw the Punnett square, you could count up the number of boxes in there that have capital R, and you would come up with 1/4. Okay, well another reason, or just to point out the reason why we do get 1/4, is that for that to happen, we really have to get a big R from this parent. Absolutely have to. And we have to get a big R from this parent. If we get this big R and we get this big R, then we're going to have that genotype that we're looking for. So in the Punnett square, that's really what's happening. We're saying, okay, from this parent, half of the time we're going to get the big R. Half the time we get the lowercase r, but we want the probability of getting capital R, so that is 1/2. Then we look at this parent and we say, what's the probability of getting capital R from that parent? Well, 1/2. So if we take the probability of event A and we take the probability of event B and we multiply them with each other, we are going to get 1/4, which is the same 1/4 that we get if we simply draw the Punnett square. Now typically, like I said, we don't use the multiplication rule when we're looking at something so simple as this, because we usually just go and we draw the Punnett square and we count up the boxes and we say 1/4. So that's where we have already really looked at the multiplication rule. If we look at another way, we can use this multiplication rule. We could look at a parent such as this one, and we could come up with the probability that that parent is going to produce a big A, big B, big C gamete. Now, if we have independent assortment, and we said that that really is a rule we're applying here in chapter 14, what happens with the A's does not affect what happens with the B's or what happens with the C's. So we can consider each one of those genes an independent event for purposes of coming up with the gamete. So we want to look at the A's individually, and we want to say, what is the probability of getting capital A? Well, we've got two different A's there, capital A and lowercase a. So half of the time we are going to pass on the capital A. For the B's, we've got big B and lowercase b. Half the time we're going to pass on the big B. And then for the C's, we only have capital C, so 1 or 100% of the time we're going to be passing on the capital C. So as independent events, we can take these probabilities, we can multiply them with each other, and in this case, we would get an overall probability of 1/4. So that would be the probability that that parent is going to produce that particular gamete. Now, one place that we do end up using the multiplication rule quite a lot when we're talking about genetic crosses is when we look at successive offspring. What we mean by successive offspring is the first offspring versus the second offspring versus the third offspring, and so on. Each one of those is an independent event, meaning that the genotypes of the early progeny, which is just another word for offspring, has no influence on the genotypes of later progeny. So what happens the first time doesn't affect what happens the second time, or the third time, or the fourth time for that matter. So if we go through and we look at some examples of using this multiplication rule, if we first go to some kind of common everyday examples, we say, okay, a couple is going to have a child. What is the probability that the couple will have one girl? Okay, well think, what are the possibilities? They could have a girl, they could have a boy. Okay, we would expect that half of the time they're going to have a girl, right? So they're having one child, could be boy or girl. We want it to be a girl, so probability is 1/2. Well, what if we say, okay, they're going to have 3, and we want to know what is the probability that a couple is going to have 3 girls? Well, keep in mind that successive offspring are independent events. So really what we're saying in this question is that we want to know the probability that the first child is going to be a girl, the second child is going to be a girl, and the third child is going to be a girl. And if they are independent events, we first want to calculate the individual probabilities of each one of those events. So first time they're going to have a child, the probability that that child is going to be a girl is 1/2. Okay, so that's the probability for the first one. When we get to the second child, it really does not matter whatsoever that we already have a girl there. So this next one is an independent event. So this next pregnancy, 1/2 chance that it's going to be a girl. Third time around, same thing, independent event, so 1/2 probability that that one will be a girl. Since they're independent events, we simply take the probabilities, we're going to multiply them together, and we're going to get the overall probability of 1/8. So if a couple has 3 children, we would expect that they have a 1 in 8 probability of having 3 girls. Now we could take the same kind of question and just write another one in here. And what if we said, okay, what's the probability that they're going to have 4 children? They're going to get 2 girls, then 2 boys. We would approach it the exact same way. If we want 2 girls and then we want 2 boys, we want the first one to be a girl, second one a girl, third one would be a boy, and the fourth one would be a boy. We go through and we figure out the individual probability of each one of these ways. Remember that each one is going to be an independent event, so 1/2 probability for each one of these, and then we would simply go through and we would multiply. Now, if you need to review your multiplication of fractions, you need to go and do that. You'll also need to look at the adding of fractions as well. So really we just multiply across the top and then we multiply across the bottom, which in this case is going to give us 1 in 16. So if someone has 4 children, the probability that the first 2 will be girls and then the second 2 will be boys is 1 in 16. So that's looking at some kind of common everyday examples. We can take the same idea and apply it to genetic crosses. So here we want to know what is the probability that that cross is going to produce a heterozygous offspring. Well, if we're just looking at this cross and we want to know what is the probability of getting this offspring, well, one simple way to approach this would be to draw the Punnett square. So we know from one parent we can have either capital A or lowercase a, from the other parent capital A or lowercase a, and then simply we go through and we fill in the boxes. After we do this, we can see that 1/2 would be expected to be heterozygous, or 2 out of 4. So 2 out of 4 reduces down to 1/2, so that would be our answer for that question. Well, what if we look at the next question? We want to know what is the probability that the cross is going to produce 3 heterozygous offspring. Well, just like before, what we're really saying is we want the first one to be like that, we want the second one to be like that, and we want the third one to be like that. Whether or not the first one is heterozygous is not going to affect if the second one is, or the third one for that matter. So we simply go through and we predict the probability of each one of those. So the probability that the first one is going to be heterozygous is a half. The second one, 1/2. Third one, 1/2. So we simply go through, we multiply them together, and we get an overall probability of 1 1/8. Okay, so if we cross those two parents with each other and we've got 3 offspring, we have a 1 in 8 probability that we would expect them to all be heterozygous. Okay, so that's using our multiplication rule. Now we do have another rule that we're going to be taking a look at, and this is the addition rule. The addition rule states that the probability that any one of 2 or more mutually exclusive events will occur is calculated by adding together their individual probabilities. So here we're talking about mutually exclusive events. So this means that it's going to happen one way or the other. So this is our or rule. We're going to take those individual probabilities. They're going to come from the multiplication rule, and then we're going to be adding them together. We use this rule whenever there is more than one way to obtain a specific outcome. So if we have multiple ways for an outcome to happen, it's not going to happen both ways. It's going to be, say, one or the other. If you go through and you figure out all of the different outcomes that could happen for an event, if you add those probabilities together, they should add up to 1 or 100%. So that's one way that you can go through and you can kind of double check yourself on these types of questions. So if we go through some examples, go back to our boy-girl example, and now we're saying, what is the probability that a couple will have 1 girl and 1 boy? Now, first off, this question is a little bit different from what we looked at before, because notice that there's not really any kind of order specified here. So really we're saying that we want 2 children and we want 1 girl and 1 boy. Well, if we're having 2 children, 1 girl and 1 boy, there's more than one way that that could happen. So if we go through and we list these different possible ways, we could have the girl first and then we could have the boy, or we could have the boy first and then we could have the girl. Either one of those possibilities would kind of answer our question here. And we're not specifying one or the other. So what we do in this case is, after we have listed the different ways that this can happen, we want to figure out the probabilities for those individual ways. That is exactly what we did with the multiplication rule. So if we just look at the first order here, the probability the first child will be a girl is 1/2. That's done and over with. The probability that the second one will be a boy is 1/2. So the probability of that way is going to be 1/4. If we look at this other order, it's going to end up being 1/2 times 1/2, which is going to give us 1/4. Okay, well, since it can be one way or the other, and both of them really meet what we're looking for here, we're simply going to take our 1/4 and our 1/4 and we're going to add them together. And when you add them together, you're going to get 2/4, and 2/4 reduces down to 1/2. So 1/2 is our answer here. Now, if you were to go through and you were to list the other possible outcomes if you have 2 children, well, if we have 2 children, we could also get 2 girls. We could also get 2 boys. For double checking purposes, if we go through and we figure out the individual probabilities of these ways, this would be 1/2 times 1/2, which is going to give us 1/4. And this one also going to be 1/2 times 1/2 and give us 1/4. And notice that if you add this, and then this one over here, all of them equal 1, or 100%. Okay, so that's a good way to double check your work if you have some extra time and you want to do so. If you figure out all the possible outcomes, then they should add up to 100%. Now, if we look at the next question, we want to know, what is the probability that a couple will have 3 girls and 1 boy? Again, we're not specifying an order. And many times in these types of questions, you'll actually see it said in any order. Okay, so if we look at this one, we want 3 girls and a boy, so out of 4 children. First approach, or first thing to do, I would say, is list the different orders. Okay, so we could have the 3 girls first and then the boy. We could have 2 girls first, a boy, and then another girl. We could have the boy second. We could also have the boy first. Okay, so if we list all our possibilities there, we actually have 4 different ways that this could happen. Any of them would satisfy what we're looking for here. So we want to find the individual probabilities for each one of those orders. That comes from the multiplication rule. So if we look at the first one, the probability the first child is going to be a girl is a half. The probability the second one will be a girl is a half. The third one a half. And then the boy on the fourth one is going to be a half. So if you go through and you add them all or multiply them all together, we're going to get 1 over 16. If you go through and you figure out the probability of the next way, going to be the same thing. We're going to get 1/16, 1/16 for the next one, and then we're going to also end up with 1/16 for the last one. Because these are mutually exclusive events, it's one way or the other, or the other, or the other, we're going to add them together. So we're adding here really 1/16 plus 1/16 plus 1/16 plus 1/16. Okay, so from here. When we add, this is going to give us 4/16, which does reduce down to 1/4. Okay, so if you have 4 children, you have a 1 in 4 probability of having 3 girls and 1 boy mixed in there. Okay, if we go and now apply this to genetic crosses. If we look at this one, we want to know what is the probability that that cross will produce 1 heterozygous offspring and 1 big A offspring. Okay, again, we're not specifying an order here. So we do have to consider the different possible ways that this could happen. We could get heterozygous first and big A second, or we could get the two the homozygous dominant first and heterozygous second. If we figure out the probabilities of each one of these ways, if I quickly draw up the Punnett square from this parent, this Punnett square is showing us the possible outcomes we can get from this cross. Gives us a good thing to look at for this question. So if we want to say what is the probability that the first child is going to be heterozygous, we look at our Punnett square and we can see that that's going to be 1/2. Probability the next one's going to be homozygous dominant. That will be 1/4. So that's because we only have 1 out of our 4 boxes that has big A. We take them, we multiply them together, and we're going to get 1/8. Okay, that's one possible order. If we look at the other one, we're going to have a 1/4 for the big A, and then we're going to have a 1/2 for the heterozygous, so that's going to give us 1/8. So we take them, we add them together, and 1/8 plus 1/8 is going to give us 2/8, and that we reduce down to 1/4. If we look at the next one, we've got 3 offspring, and we want 2 that are big A, and 1 that is little a. Write all the orders out. Okay, so if we write out the different orders, okay, that would be one order. We could have the little a in the middle, and we could have little a could be the very first one that we have. So with this one, we would go through and we would figure out the probability of each one of the orders. So probability of getting big A from these parents is 1/4. Probability of big A again is 1/4. And then for little a is actually going to be 1/4 as well, because we have that bottom box there. So we go through and we multiply them together. When we do that, we multiply across the top and then we multiply across the bottom. And on the bottom there, we're going to end up with 1/64. When we look at the next order, it will come out the same, 1/4 times 1/4 times 1/4. So we're going to get another 1/64. And on the bottom, you will get another 1/64. When you take these and you add them together, we're going to get 3/64. Okay, so that would be our answer there on that one. So all of this is throwing the addition rule in there. Notice the difference between the addition rule versus the multiplication rule. The multiplication rule is just talking about independent events. When we think about independent events, we're talking about successive offspring, one offspring versus the next offspring or the next one. And then we can also use it if we're talking about multiple genes, because if we have independent assortment, they are independent events. Okay, so these rules, multiplication rule and addition rule, they're very helpful because they can be used to predict the outcome of genetic crosses. If we're dealing with a dihybrid cross, so 2 genes at once, or even a larger cross than that, it becomes relatively simple because it's equivalent to 2 or more independent monohybrid crosses occurring simultaneously. So if we have a cross like this, in calculating the chances for various genotypes from such crosses, each character first is considered separately, and then the individual probabilities will be multiplied together. So to take a look at what we mean, if we go back to the dihybrid cross, for this question, we've got our parents here, and we want to know if we cross those parents, what is the probability, first off, of getting this particular offspring? Well, one approach for that would be to draw the Punnett square, fill in all of the boxes, and count up how many of the boxes actually have big A, big B, little b. A simpler approach would be to use our probability rules. We're looking at 2 genes here, and they assort independently. So what happens with the A's doesn't really affect what happens with the B's. So we're going to look at them separately. If we first look at the A gene, we're going to come up here and look at our parents and look at what they had for the A gene. So really, this is the cross that we're making. And over here, we're saying we want to know what is the probability we're going to get big A from those 2 parents. So if we draw the Punnett square here, we can see that from these parents, we actually have a 1/4 or 1/4 chance of getting big A. So I'm going to write that over here underneath the A's. That's the probability for the A's. Then we want to look at the B's. So now we ignore the A's. We look over here and we look at what our parents are for B. They're both heterozygous. And we want to know what's the probability of getting heterozygous offspring from them. Okay, again, you can draw that little Punnett square, which is going to be like this in this case. And we look at how likely it is we're going to get heterozygous. So in this case, we've got 2 out of 4, which is going to give us 1/2 for the B's. So I go over here and I write my 1/2. Well, now, since they're independent events, we simply multiply them together and we get an overall probability of 1/8. Much simpler than going and drawing out the huge Punnett square. If we look at the next one, okay, very similar. We would just evaluate the probability for the A's. We could come back up here and see that for our A's, we actually have a 1.5 probability of getting heterozygous. And for the B's, if we go over here, we can see we've got 1/4. So again, we multiply them together and our probability would be 1/4. Now, when we drew up Punnett square before, when we looked at this one, we said, what's the probability of getting this offspring? Okay, and we counted up the different boxes and we came up with 1/4. Well, if we do it using our probability rules, first we would look at the D's. Okay, so we look at our D parents, which happen to both be heterozygous. And we want to know the probability of getting heterozygous offspring. We draw our mini Punnett square. And we can see that we've got 1/2 for our D's. Then we look at our E's. Both of our parents are heterozygous for E, and we want heterozygous offspring here. So again, we draw our mini Punnett square. And we can see in our mini Punnett square that, again, it's going to be 1/2. So we've got a 1/2 for our E's. 1/2 times 1/2 is going to give us 1/4. Okay, so notice we would get the same answer if we did it either way, but I would highly recommend that you use the probability rules. I think that it will eliminate a lot of careless errors that come into play when we do start drawing those big Punnett squares. So if we look at this one, slightly different type of question. We've got the same cross, and we want to know what is the probability of getting one offspring that has the dominant phenotype for both genes. So now we're actually looking for a phenotype. We want it to be dominant for both genes. So notice what we're saying is that we want it to have the dominant A phenotype, and we also want it to have the dominant B phenotype. Well, if we wanted to have the big A look, really we want at least one capital A. For the big B look, we really want at least one capital B. Once we know that, we can approach this the same way that we just did. We look at the A gene first and we look at our two parents. This is what they are. And we say, what is the probability when I draw that little Punnett square that I'm going to get this? Okay, so when you do that, you will come up with 3/4. Okay, so 3 out of the 4 boxes are going to have a big A in them. So 3/4 is our probability for the A. And then for the B's, we would do the same thing. And we want it to be like this. And when you draw that Punnett square, which I'll let you do on your own, you also get 3/4. So we've got 3/4 for our B's. If we multiply across the top and across the bottom, we're going to get 9/16. Okay, so that's the probability for that one. That if we do that cross, the probability of getting one offspring that has the big A and the big B look is going to be 9/16. Now the next question ties a lot of it together, saying what is the probability of getting one offspring that has a dominant phenotype for both genes and one offspring that has the recessive phenotype for both genes. To make it a little more difficult still, notice that there's no order that's specified in this question. So we've also got multiple orders thrown in here as well. So if we write out our different orders to start with, we could have the offspring that's dominant for both, could be first, and then we could have the one that's recessive for both, and that could be second. Or we could have the situation where we have the one that's recessive for both first, and then we could have the dominant one second. Well, if we figure out the probability of the first one, well, that's what we already figured out up here. So the probability of having an offspring that's going to be dominant for both is 9/16. Now we need to know what's the probability that an offspring would be recessive for both. Well, for an offspring, if we just draw it up here, to be recessive for both, it's going to have this combination. That's the only way that we're going to be recessive for A's is to have the 2 lowercase a's, and the only way we're going to be recessive for B is to have the 2 lowercase b's. So we go back to our parents here, okay, which came from up here, and we say, what is the probability of getting little a from that? If you draw the Punnett square, you'll find that it's 1/4. Okay, then we look at the B's. Both parents are heterozygous. We want to know the probability of getting little b, and it is 1/4. When you multiply that together, we get 1/16. So the probability that we're going to be recessive for both is going to be 1/16. Okay, so if we go and we multiply those together, we're multiplying across the top and we're multiplying across the bottom. And so we are going to get a 9 on the top and a 256 on the bottom. That's the probability of that particular order. Now we have to consider the other order, other way it could happen. So over here, the probability it will be recessive for both is 1/16. The probability it will be dominant for both is 9/16. Multiply them together, and we get 9/256. Well, since it can be this way or this way, we're going to take those two, we're going to add them together, and we end up with 18/256. Now that does reduce down slightly. It's going to be 9/128. And that right there would be our final answer to that particular question. So notice how we've got some multiplication rule mixed in there. We've also got some addition rule mixed in there as well. If we look at this question here, if we have this particular plant and it is self-fertilized, we want to know what is the probability of getting a quadruple heterozygote offspring. Okay, well this question, we're really taking this parent, we're selfing it, which means we're crossing it with itself, and we want to get that offspring that we've written there, which really is exactly like the parents. we look at this question, we approach each gene individually. So we've got 4 genes involved. We really got 4 kind of mini monohybrid crosses buried in here. So first we look at the A's, and notice that we're heterozygous for A's for both parents. So if we draw the A monohybrid cross over here, those are our parents, and we want to know the probability of getting heterozygous from that cross. You can draw your little Punnett square, count up the number of boxes in there that are heterozygous. You should find that you've got a 1/2 there for your A's. And then we can look at the B's. Okay, and we want to get heterozygous for B. So here's our cross. Here's what we want. Draw your Punnett square and come up with the probability. Should be 1/2. When we do it for the C's, we're going to get 1/2. When we do it for the D's, we're going to get 1/2. And then we would simply multiply across, and that's going to give us 1/16. Okay, so that would be our probability there. What if you were asked how big that Punnett square would actually be if you were to try to approach it by drawing a Punnett square? Okay, if we want to predict the size of the Punnett square, we have to predict how many different gametes we could get from each of the parents. So if we look at this parent here, there's 2 different A's, 2 different B's, 2 different C's, and 2 different D's. So there's actually 16 different gametes from that parent. And if we do the same thing over here, this one's going to produce 16 as well. So the size of the Punnett square is 16 times 16, which is 256. That's a pretty big Punnett square. So that should help emphasize to you why you do need to learn the probability rules, because you are definitely not going to have time to draw a 256 box Punnett square when you take this exam for chapter 14. If we look at a couple of human traits here, widow's peak is a dominant trait in humans. So that means that having a widow's peak is dominant, not having a widow's peak would be recessive. So we want to assign a letter here to use. I'll just pick A for simplicity. And we're going to have 2 versions of A. We've got capital and we've got lowercase. Capital A is going to be having a widow's peak, and that's because we're told that widow's peak is dominant, and no widow's peak is going to be our lowercase a. So we want to know, what is the probability of these parents producing 2 children with no widow's peaks? Well, we have to figure out what the genotypes of the parents are initially. The woman, we're told, is heterozygous, so that tells us she's like this. She's going to marry a man who does not have a widow's peak. Well, keep in mind that if someone does not have a widow's peak, they can't have a capital A. So the only possibility for the father is 2 lowercase a's. So we want 2 children with no widow's peaks. So if we do this cross, let's see, first one we want no widow's peak, and second one we want no widow's peak. So when we do this cross, we put the gametes from one parent on one side, gametes from the other parent on the top, and we fill in our boxes. Okay, so after we get our boxes filled out, we can look at which ones actually don't have a widow's peak. It's going to be these 2 bottom ones. Okay, they have no widow's peak, so that's going to be 1/2. And then the next time we have a child, probability that there's no widow's peak will be 1/2. So it's simply 1/2 times 1/2, and that gives us 1/4. So that's our overall answer there. Well, if we look at the next one, we say, what is the probability of these parents producing 2 children with widow's peaks? Well, very similar question, because now we just want them to have a widow's peak basically both times, the first and second time. We go back to our Punnett square we drew before, because it's the same parents. This one would have a widow's peak, and so would this one right here. So the probability the first one would be 1/2, and the probability the second one would be 1/2. So the probability that they both have widow's peaks is going to be 1/4. If we throw in just one more gene into all of this, we've got our widow's peak. Now we're going to have an earlobe gene. So widow's peak, if we go back and we write our A's over here on the side, we said capital A was going to be widow's peak, lowercase a is going to be no widow's peak. Now we've got a B gene for our earlobes. We're told that free earlobes are dominant, so that means that capital B is going to be free, and that means that attached is recessive, or going to be our lowercase b. So we want to consider that we have a woman with no widow's peak and attached earlobes. If we stop right there and come up with her genotype, this woman has no widow's peak. The only way she can have no widow's peak is to be 2 lowercase a's. And she also has attached earlobes. The only way she can have attached earlobes is to be 2 lowercase b's. We're going to take her, that's our woman. We say that she marries a man that is heterozygous for widow's peak. So he is going to be a big A, little a. And he's homozygous for free earlobes, which means that he must be the 2 capital B's. Once we've got that, it becomes a pretty straightforward question, hopefully. We want to know what is the probability of these parents producing a child with a widow's peak and free earlobes. Okay, so if we talk about what we're looking for, we want the child to have a widow's peak, so that's the dominant look. At least one big A is going to give us that. And we also want them to have free earlobes, and 1 capital B is all they need for that. So that's the genotype we're looking for here. We look at the A's first. This would be our cross of the A parents. If we draw that Punnett square, notice here the probability of actually having a widow's peak is going to be 1/2. And then if we look at the B's, now you could draw a Punnett square for this if you wanted, but notice we only have 1 kind of B from here and there's only 1 kind of B from here. So it is heterozygous, which more appropriately we would write in the other direction. And so what that means is that we have a 1 or 100% chance of having free earlobes in the offspring. So that's going to, when we multiply it together, give us an overall probability of 1/2. If we look at the question right below that, we want to know what is the probability of these parents producing 2 children with attached earlobes and no widow's peaks. So we want these children to have attached earlobes, which is the lowercase b, and we want them to have no widow's peaks, so we want it to have little a, little a. Well, if we look at we want 2 children like that. We look at the probability that that first one will have a widow's peak. The probability the first one's going to have a widow's peak would be 1/2, and the probability that that child's going to have attached earlobes, if you look up here, we just said that when we cross these parents 100% of the time, they're going to have the free earlobes. Okay, so this is 0 here for our probability. To figure out the probability of that particular way, we would multiply those together and we would get 0. If you look at the other one, it's going to be, again, 1/2 times 0 to give us an overall probability of 0. And when we multiply anything by 0, we get a 0. So you have a 0% probability that those 2 parents are going to have attached earlobes and no widow's peaks. So that's our run through of the probability rules. With this section on genetics, it is critical that you go through and you work as many questions really as you can possibly do. There are many practice questions up there on Angel. There's also keys available with them, as well as what we call PenCast, which show the solving of many of the genetics questions. So I strongly encourage you to go through and try those different questions, see if you can come up with the right answers on your own when you're not being guided through them. And then also try out those practice quizzes on Angel as well to make sure that you understand them.